Hello, everyone. In this lesson, let's study the functions and application of the stepper controller and the stepper motor. In this lesson, we will learn from the composition of stepper motor, stepper controller module cabling, wiring, dip switch setting, and motor wiring. Through the study of this lesson, I hope that everyone can correctly complete the wiring of the physical stepper motor and stepper controller according to a practical case of using a stepper motor and a stepper controller, correctly complete the setting of the dip switch, complete the wiring and power on debugging of the physical stepper controller, and experience the use of the stepper motor and the stepper controller. It can cultivate scientific thinking and sense of responsibility, and stimulate rigorous attitude and innovative spirit towards engineering and technical problems. Let's learn the first part. Stepper motor is an open-loop control element that converts electrical pulse signal into angular displacement or linear displacement. Stepper motor is an induction motor. Its working principle is to use electronic circuits to convert DC power into multi-phase timing control current supplied at different times. Only by using this current to power the stepper motor can the stepper motor work normally. The driver is a multi-phase timing controller that supplies time-sharing power to the stepper motor. When the stepper driver receives a pulse signal, it drives the stepper motor to rotate a fixed angle, i.e. stepping angle, in the set direction. There are three types of stepper motors: permanent magnet, PM, variable reluctance, VR, and hybrid, HB. Permanent magnet stepping is generally two-phase with small torque and volume, and the stepping angle is generally 7.5 degrees or 15 degrees. Variable reluctance is generally three-phase and can achieve large torque output. The stepping angle is generally 1.5 degrees, but it has loud noise and large vibration. It has been eliminated in developed countries such as Europe and the United States in the 1980s. Hybrid stepping refers to the mixture of the advantages of permanent magnet and variable reluctance. It is divided into two phases and five phases. The two-phase stepping angle is generally 1.8 degrees and the five-phase stepping angle is generally 0.72 degrees. This kind of stepper motor is the most widely used. Stepper driver module interface function. Interface P1 function introduction. There are 6 interfaces in total. The first and second are pulse signals. The pulse signals are used to control the operation of the motor. The rising edge is effective. The high level is 4 to 5 volts, the low level is 0 to 0.5 volts, and the pulse width is greater than 1.5 microseconds. The third and fourth are direction signals. The direction signals determine the forward and reverse directions of the motor. The high and low level switching needs to be established 5 microseconds before the pulse signal. The initial running direction is changed by interchanging phase windings. The fifth and sixth signals are enable signals. The enable signals control the working state of the driver. The high level is enabled, the low level is disabled, and the suspension can be automatically enabled to ensure that the motor runs on demand. The wiring is as shown in the figure. The first interface is connected to Q0.3, the second interface is connected to 0V, and the rest are not connected. Interface P2 function introduction. There are 6 interfaces in total. The first and second are power interfaces, which provide DC power supply, ranging from plus 20 volts to plus 50 volts. Plus 36 volts DC is recommended to ensure the stable operation of the motor and avoid insufficient or excessive voltage affecting performance. The third and fourth interfaces are the A- and A+ interfaces. The fifth and sixth interfaces are the B- and B+ interfaces. The physical wiring is as shown in the figure. The first and the second grounding wires are connected to 24 volts power supply voltage plus. The third is connected to the A-, the fourth is connected to A+, the fifth is connected to the B-, and the sixth is connected to B+. Stepper driver module cabling requirements. M542 driver adopts differential interface circuit, which can be applied to differential signal, single-ended common cathode or common cathode interfaces. Built-in high-speed optical coupler allows the signals of long wire driver, open collector circuit and PNP output circuit to be connected. The long line driver circuit is used in harsh environment, and it has strong anti-interference ability. Now take the open collector circuit and PNP output as examples. The interface circuit diagrams are shown as follows. Figure A shows the open collector, common anode, and Figure B shows the PNP output, common cathode. Anti-interference cabling measures. It is recommended to use twisted pair shielded cable. The shielding layer is connected to the ground wire to ensure good grounding and prevent interference. The shielding layer is not connected when it is not a real grounding wire. The pulse and direction signal lines are separated from the motor power line by at least 10 centimeters to avoid motor noise interfering with the signal and improve the control accuracy. Safe operation requirements. Do not plug and unplug the P2 terminal while it is powered on, otherwise it will damage the driver. Ensure safe operation and prolong the service life of the equipment. Select the appropriate resistor according to the DCC value. Short circuit at 5 volts, 1 k-ohms at 12 volts, 2 k-ohms at 24 volts. Ensure that the power of the resistor meets the requirements and avoid overheating damage of the resistor. Check carefully after the wiring is completed to ensure the correct connection and avoid abnormal operation of the motor or damage to the drive due to wiring errors. Stepper driver current and subdivision DIP switch setting. The M542 driver uses an 8-digit DIP switch to set subdivision accuracy, dynamic current and half current or full current, as shown in the table below. Current setting, SW1 to SW3, 3-digit DIP switch is used to set the motor running current, dynamic current. For example, the average current is 1.7 amperes. SW1 and SW2 are OFF, and SW3 is on. The 4th digit SW4 DIP switch is used to set the stationary current, static current. The SW4 DIP switch sets the static current. Off is 60% of the dynamic current. On is the same as the dynamic current, and is generally set to off to reduce heat generation and improve reliability. Subdivision setting. The subdivision accuracy is set by the SW5 to SW8 4-digit DIP switch. The subdivision multiple is set through the SW5 to SW8 4-digit DIP switch, from 2 to 125. The higher the subdivision multiple, the higher the motor control accuracy, but the current consumption also increases. The subdivision multiple affects the number of steps or turns. Combined with the sprocket transmission ratio and motor reduction ratio on the object, the motor rotation angle can be accurately controlled to meet the needs of different application scenarios. For example, the subdivision multiple is 40. Originally 1.8 degrees per 1 pulse, 200 pulses, equals 40 * 200 equals 8,000 steps a turn. SW5 and SW6 are on, and SW7 and SW8 are off. The stepper drive is wired to the motor. Different motor wiring methods include 4-wire wiring, 6-wire wiring, and 8-wire wiring. This example uses 4-wire motor wiring. Wiring diagram and precautions. Provide detailed driver and motor wiring diagram. Ensure that users can wire according to the diagram, and avoid equipment damage or abnormal operation caused by wiring errors. The calculation of the number of rotation pulses of the stepper motor. The formula for calculating the number of pulses is shown in PPT. The formula for calculating the number of rotation pulses is P1 equals P2 times R2/R1, where P1 is the number of PLC output pulses, P2 is the number of subdivisions, R2 is the rotation radian of the controlled object, and R1 is the rotation radian of the motor. In the formula, P1 represents the number of pulses output by PLC. P2 represents the number of subdivisions set by the stepper driver. R2 represents the radian, rad, of the controlled object rotation. R1 represents the radian, rad, that the stepper motor needs to rotate. I1 represents the gear ratio of the sprocket on the object, 19:49. I2 represents the reduction ratio of the stepper motor, 130 or 136. And 360 represents 360 degrees rotation of the motor. The sprocket transmission ratio I1, 19:49, and motor reduction ratio I2, 130 or 136. On the object affect the calculation of pulse number, so it is necessary to accurately input the transmission ratio parameters to ensure the accurate calculation. Example: a certain stepper motor rotates 1/4 revolution, subdivides 40 times, and has a total rotation of 8,000 steps. Please calculate the number of pulses of the PLC. P1 equals P2 times R2, or R1 equals 8,000 x 90 or 360 is equal to 2,000. Now let's take a look at the actual operation. This is the physical stepper motor and stepper controller. Physical wiring of step controller, 2 P1 wires. The first one is connected to Q0.3 of PLC. The second wire is connected to the ground wire 0V, and the rest are not connected. Connect 6 wires to P2. Connect the first to the ground wire. Connect the second to the 24 volts power supply voltage plus. Connect the third to the A-, connect the fourth to A+, connect the fifth to the B-, and connect the sixth to B+. Settings of the DIT switch. SW1 and SW2 are off, and SW3 is on. SW4 is off. SW5 and SW6 are on, and SW7 and SW8 are off. Finally, please think about this course and complete the following exercises, aiming at consolidating the knowledge points you have learned today and further deepening your understanding. This lesson ends here. See you next time.